So we are starting right at 2:30
Yay!
on the solids. We're going to talk about solids. So this, like I said in class today, this is kind of an important one for the new AP exam. Or it appears to be, at least. We'll have to wait and see after a couple of years of testing. But they have a lot of stuff in the essential knowledges and learning objectives about this. So we're going to spend some time on it. The two basic groups for solids are crystalline and amorphous. Okay, I guess we're going to do an example of crystalline first. So an example of a crystalline solid, that's where it's very ordered, very neatly arranged. One example of that is quartz, SiO2, silicon dioxide. That's what quartz is. Another example is amorphous, and an example is quartz. So there you go. It just depends on the arrangement of the SiO2. It can arrange itself amorphously or morphously, I suppose, or in a crystalline structure. So, yeah, it's the definition of amorphous means that you can go through the molecule or through the substance, whatever it is, and you're not going to see a regular repeating pattern. So if you move through this thing, you know, it does look kind of regular, I suppose, but, you know, depending on what angle you move at it, or move through it at, that's awkward, you may not get the same thing as you go through, right? Now over here, if you look at the crystalline, I mean, it's very highly ordered, so you know that every time that every direction you move through this thing, you're going to see this ordered arrangement of hexagons, okay? And so that's kind of the idea there, between the difference between crystalline and amorphous, okay? Most of the things we talk about are crystalline in structure. Glass is a really good example of an amorphous solid. Any of you heard that glass is a liquid? Okay. I actually read something a couple of years back, because I'd been telling my students for years that glass is a slow-flowing liquid. What they actually decided was, no, it's probably not. It's probably just an amorphous solid. And one of the big arguments for glass being a liquid was that if you look at these old 18th, 19th century homes in the United States, the glass at the bottom is thicker than the glass on top in some of those houses. And so the idea was, oh, the glass is flowing slowly over time. Well, then people started thinking about it, and they're like, well, you know, they probably didn't have a way to manufacture glass perfectly to have the same thickness all throughout back then. And so where are you going to put the thicker part of the glass? Probably on the bottom, right? So they think that's probably more what was going on there rather than the glass actually flowing. So anyway, I mean, that has nothing to do with anything, but it's kind of interesting. So you have ionic crystals. Now, some of this stuff you don't need to write down because they specifically say on the AP objectives, they say you don't need to know about the different types of cubic arrangements, or the different type of crystal arrangements in the ionic compounds. And I never really taught that in detail anyway because I had never seen a question about it. They're just making it more specific now. They're not going to test on that. So just to give you an idea, this is called the unit cell. The word that you probably do need to know is crystal lattice. Okay? And a crystal lattice, that's one of your vocab words in the reading guide. So I would know that one. And basically a crystal lattice is just the idea of the structure that gets formed by an ionic compound when the ions arrange themselves in an orderly pattern. Okay? But there are some different ways that those arrangements can occur, and you don't need to know any of these names. Okay? And then this is just showing the types of arrangements and how you can actually use these arrangements to figure out the empirical formula of the ionic compounds. But again, we don't need to do this because it's not going to be on the exam. Now this is useful, okay? This is where we start talking about the 4 basic types of metallic solids that you need to know. I said metallic, sorry. The 4 basic types of crystalline solids that you need to know. One is molecular. Okay, molecular is, that's either atoms or molecules, and these are just connected with London dispersion forces for the most part. You can also have dipole-dipole forces. There are hydrogen bonds. Okay, so that's your typical molecular compound: carbon dioxide, hydrochloric acid, those sorts of things. They give a bunch of examples over here. Actually, methane gas, sucrose, which is sugar, which is C12H22O11, argon gas. So those are some examples of molecular solids. Okay, molecular solids tend to be either gases or liquids at room temperature, or if they are solids, they are those intermolecular forces are usually fairly easily broken. Now, not always. You get up to a big compound like sucrose, okay, and that's fairly solid at room temperature because it's just so big. It's got London dispersion forces. It's got some dipole-dipole happening there. So the bigger these molecules get, the more likely they are to be a solid at room temperature. But most of the time they'll have relatively low melting points if they are solids, unless you're talking about a really big compound, and then they might not. Okay. Covalent network solids. There are really two examples you need to know for covalent network, and actually we're going to go through these more. I should probably not spend so much time on this one slide where you can't really even read it. But covalent network, everything's connected in a network of covalent bonds. These aren't intermolecular forces. These are actually covalent bonds. Okay, and so it's actually going to be a lot stronger. And examples of that would be diamond and quartz. So that's why they're so hard. Ionic compounds, I think we're pretty familiar with those. You've got positive ion, the cation, and the negative ion, the anion, and they're attracted to one another, and they form these arrangements of ions. And then metallic, I described that last year as a hippie commune, where all of the positive nuclei are sort of lined up, and they share valence electrons between them. So the valence electrons don't necessarily belong to any one particular atom necessarily. They kind of have the ability to flow. Okay, so covalent network and molecular solids. So diamonds are an example of a covalent network solid. Those are going to be hard and have high melting points. I mean, it's kind of an understatement. Diamond is the hardest material. So diamonds are covalent networks. So notice here, this is diamond, okay? And so it's basically, it's a bunch of carbon atoms, and they're all connected with covalent bonds, and that's all it is, okay? And so that's why it's so strong, because in order to even melt this thing or break it at all, you have to break covalent bonds. Now graphite, on the other hand, it's a molecular solid, and the atoms are held together with van der Waals forces, which this set of notes is calling London dispersion, LDF, calling it van der Waals. Graphite is really soft. They're both made out of carbon, right? One is carbon that's covalently bonded. That's diamond. The other one is carbon that is, actually, the carbon here is covalently bonded within the plane, but in between the planes, it is intermolecularly bonded. It's bonded with just intermolecular forces, okay? In other words, LDF. So that's why it's easy to actually push the layers apart, and that's why graphite crumbles the way that it does when you use it to write, okay? So you've got an example there of, you know, based on the way that a particular atom is arranged, it can have very, very different properties, okay? And I think we've talked about this before a little bit, haven't we? When we talked, because we talked about graphene and the nanotubes and all that stuff. Okay, and then metallic solids. The metals are not covalently bonded, but you've got these really strong attractions here, so you're not going to call them van der Waals forces either. But what's going on here really is just a lining up of all of these atoms, and then the electrons are free to kind of flow throughout. And that's for reasons that we're not really going to go into. If you are interested in it, it is in the book. And it goes a little bit more into the molecular orbital theory of these things. Let me find what page it's on. Okay, here we go. It's on 992 and 993 in the book, in case you're in case you're interested in that. It talks about the electron C model a little bit more, which is what they're basically showing here, the electron C model. And that's the one that kind of fits well with the Lewis, the valence bond theory that we've talked about for most of the year. But then they also talk about the molecular orbital model and how that works. And that does a little bit better job of going into the explanation for why these things end up being this sea of electrons, why the electrons become so delocalized and they're able to move wherever they want to move. So if you're interested in that, you can look there in the book. But because they are delocalized, really? Okay, we're going to talk a little bit more about this because I want to go through the actual AP curriculum because they do a better job of getting in depth here. But because these electrons are delocalized, that's why metals are such good conductors of electricity. It's also why they're so malleable. So you hit this thing, and the electrons kind of have the ability to sort of flow out of the way. Okay, so you get something that's a little bit more fluid than a normal brittle solid like an ionic compound. You hit an ionic compound, and actually, you know what? That's in the AP thing too. So I'm just going to show this to you because the notes, the book, do an okay job of introducing these things, but it appears that they want a much higher amount of depth as far as what you know about these things. So I'm just going to talk a little bit about this now. And let me see if I can find where I need to be. That's covalent bonding, ionic bonding, metallic bonding. I just need to look at that's a little bit of it right there. But I need to just look at the notes that I gave you today and make sure that I hit on some of these. All right, so starting with number 14 on your reading guide. Well, now I'm going to start really with 2C3, I think. Yeah, where it starts talking about metallic bonding, okay? So metallic bonding, it says, describes an array of positively charged metal cores surrounded by a sea of mobile valence electrons. Okay, so you can see how the wording that they're using there. But the valence electrons from the metal atoms are considered to be delocalized, not associated with any individual atom, i.e. hippie commune. Okay. B, metallic bonding can be represented as an array of positive metal ions with valence electrons drawn among them as if the electrons were moving, so as if they're kind of able to flow a little bit. And that can explain a lot of properties of metals, which I already talked about, why they conduct so well. Malleability is, they bend without breaking when you hit them. Ductility, that means you can draw it into a wire, so you can pull it really long before it breaks. And low volatility, which means it doesn't, metals don't tend to evaporate at room temperature. That's because they're, the electrons have a high attraction for the metal cores, okay? So the number of valence electrons involved in metallic bonding via the shell model could be used to understand patterns in these properties and could be related to the shell model to reinforce connections between metallic bonding and other forms. So we might talk a little bit, this is where you get into some of the transition metal patterns that can occur. And I actually didn't read over that one very closely. I probably should put that on your activity for tomorrow to make sure that we can talk a little bit about some of those trends maybe between the metals and why some of them in the transition area behave the way that they do. This is a really cool area of chemistry, and there's a lot that can be done here, talking about transition metals and why they change the color that they change and why they do the things that they do and that sort of thing. So it's good stuff, but we don't have time to go into a lot of detail on it. But I did want you to see that. And then we've got 2D 1A.
when you're talking about the sea of electrons,
Uh-huh.
different from electron cloud.
Yes. Okay, so the question was sea of electrons versus electron cloud. So sea of electrons exists between different nuclei, okay? So this is actually a bond between nuclei. The electron cloud, we're just talking about one atom and the electrons that surround that one atom, okay? So the sea of electrons really is created by several of these electron clouds coming into contact with one another and then forming a bond, okay? And again, we're not going to get into a lot of detail about how that happens. If you want to read about it, it's in chapter 23, those pages that I gave you in the book. It kind of explains a little bit more how the orbital overlap works there and how it gives those electrons a place to essentially travel in between the different atoms. Okay. Type of bonding in a solid state can be deduced from its properties. And then you get down, okay, so here's where you can kind of see they just start going into a lot of detail about all of these things. So you've got ionic solids have high melting points, are brittle, and conduct electricity only when molten or in solution. So there's some things they want you to know there about ionic compounds. Many of these properties are related to their structure. Obviously, they have low vapor pressure because they're so attracted to one another, so they're not going to evaporate. They tend to be brittle. I like this explanation here. They tend to be brittle due to the repulsion of like charges caused when one layer slides against another layer. Okay? So if these things are basically arranged in a perfect pattern so that the positives and the negatives are kind of alternating in all directions, as soon as you break that, as soon as you kind of slide them in the wrong direction, then there's going to be this repulsion that breaks them apart. Okay? So that explains part of why they're so brittle, because you hit these things and they just shatter. As opposed to a metal, because these metals have just this sea of electrons that you can almost think of as fluid a little bit. So you hit it and it can kind of move out of the way and then come back. Okay? That doesn't happen with ionic solids. Ionic solids do not conduct electricity because in order to conduct electricity you have to have the movement of ions. Okay? So if you melt them or dissolve them in water, then those ions are free to move, and then you can have electricity. That's actually what number 4 says, when you dissolve it in water. Dissolving a non-conducting solid in water and observing the solution's ability to conduct electricity is one way to identify an ionic solid. Ionic compounds tend not to dissolve in nonpolar solvents because the attractions among the ions are much stronger than the attraction among the separated ions in the nonpolar. So in other words, if you put it in something that's nonpolar, then they're not going to want to separate from one another. It takes something very polar like water to be able to pull those ions apart from one another to form those ion-dipole bonds. Okay? And then the attractive force between any two ions governed by Coulomb's law. And we've talked about this part a little bit. Now here's the exclusion statement that basically says the study of specific varieties of crystal lattices for ionic compounds is beyond the scope and course of the AP exam. Okay? So it actually says here, this is kind of what I said, the topic has not been part of the AP chemistry exam for many years, and including it in the new course is not really seen as important. So that's why. Okay? If you want to look at that stuff, you can. It becomes fairly useful when you're talking about geology. If you're studying rocks and how they break, then that comes into play. But for this class, we're not really going to talk about it. Then you've got 2D2, okay? Needs to be an R in front of that. Sorry. Okay, anyway, metallic solids are good conductors of heat and electricity, and so it talks about some of the properties of a metallic solid that you need to know. They actually have a wide range of melting points. Now give me an example of one that shows that there's a wide range of melting points. Mercury, right? Mercury is a liquid at room temperature. It's a metal. Our son knocked the thermostat cover off our thermostat the other day at our house, and so I was just sitting there fascinated for a while watching the mercury go back and forth in a little tube. Anyway, it's neat. I like mercury. I wish it wasn't so poisonous. Metallic solid can be represented as positive kernels. So if you want to think of it as popcorn, then there you go. or cores. So that they might call it kernels or cores. You need to get used to that terminology a little bit. On the AP exam, they seem to, or in the new AP curriculum, they seem to like to refer to the nuclei as a positive core. So, I mean, it kind of makes sense, but just kind of different terminology than we're used to, I think. Consisting of the nucleus and the inner electrons of each atom surrounded by a sea of mobile valence electrons. So then this talks a little bit more about, interesting. I did not actually notice this when I read through it earlier, that you need to know the difference between interstitial and substitutional alloys. So we're going to have to talk about that. Make sure that I should have put those in the definitions for this section. Maybe you can add those to your definitions on the front page. Because that evidently is something they now want you to know. And I actually, I don't remember if I quizzed you guys on this. I think 2 years ago I quizzed them on this in Honors Chem. And then I decided not to because I thought it wasn't necessary, but evidently now it is. Oh, so did we talk about it last year? Okay. So we might have talked about it a little bit. But anyway, evidently that's something you need to know now, and I didn't even catch that was there. So then it talks a little bit more about alloys, which would be good to know. When you form alloys, obviously it can alter some of the properties as far as the conductivity and those sorts of things. Okay. Sorry, I'm trying to rush through this because we need to be done pretty soon. Covalent network solids. So it talks a little bit more about covalent network solids and how those work, so you might read through that. Graphite is an allotrope that forms sheets of two-dimensional networks. So you've got a covalent network in one dimension, okay, I guess in 2 dimensions, but then in that third dimension you've got just London dispersion forces between the layers, okay. Silicon, it talks about being a covalent network solid. So they want you to know diamond, they want you to know silicon, silicon dioxide, quartz. Talks about some more interesting stuff there. Molecular solids with, okay, so then it talks about just molecular solids in general. So you can see how, I mean, there's a lot in the AP curriculum about these 4 types of solids. So they really do want you to know these well. So I would just take some time to take a look at these, read over them all. And I gave you a place on your reading guide, actually, to take notes over all 4 of those different types of solids from the AP curriculum, because I thought that was important to supplement, because I'm not sure that the book goes into quite that much detail. Okay, so that's that. We will talk about this tomorrow in class. See you later.